So picking up where we left off with the college algebra review topics, we're going to take a look at this left column of radicals. If you can't remember how to work out radicals, that's okay. Go to your calculator, type in the square root of 36. The answer should be 6. Because what this means is what number times itself would give us 36, and that's a nice number of 6. So 6 ends up being a rational number. It ends up being a whole number. It ends up being an integer, a lot of different things. Okay, let's look at 24. This says, let's find the square root of 25 minus the square root of 16. Remember, the square root is a grouping symbol, so we have to do this radicals first. So the square root of 25, if you compute it on your calculator, works out to a nice number. It's 5 minus square root of 16 is 4, so the final answer is 1. Okay, look at 25. Try that one on your calculator. Do the square root of 50. So second, x squared, 50, close your parenthesis. Notice that we end up with an irrational number. That number never repeats, nor does it end. So what do we do with square root of 50? Well, we try and simplify it. Kind of think about simplifying something such as a fraction. If we had a fraction such as 4/8, okay, it's common practice not to leave it unsimplified. We usually divide out a common factor of 4. Oops, makes that 1. Divide out 4 into 8, make that a 2. Okay, so our next thought is, since this is not a rational number, it's irrational, is there some way we can simplify it, which would include a radical in the answer? So what we do is we think about square root of 50, and we look at the factors of 50. Well, 5 times 10 make 50. So that's something we might want to do is break 50 down into factors. 5 times 10. Okay, but what we want to do is we want to divide out all the factors that we can. We want to simplify this. 5 times 10 can be thought of as the square root of 5 times. Now, 10 isn't all the way broken down, but we can make that 5 times 2. So what we do to simplify a radical is we look for factors of 50, and we break that all the way down till it's what we call prime factor. And then if you have repeated factors, which we do, we have 2 5s and only 1 2, okay, we can think of this as the square root of, if you want to, 25 times 2. Now, could I have gone from here to here? Sure, I could have. I'm looking for a perfect square. Okay, so 25 times 2 does give me 50, as does 5 times 2, and this kind of helps us see it better. Okay, so now what can we do? There's a property of radicals that say if you're multiplying in here with factors, that you can break apart those factors and give them each their own radicals. So in this case, do we know what the square root of 25 is? We sure do. Square root of 25 is actually going to simplify to 5. What do we do with the square root of 2? Well, we keep it as part of our answer. So this is actually an exact answer using radicals in our answer. So let's look at 18. Square root of 18, square root of 18. If you did that on your calculator, you're going to get an irrational number, a decimal that never repeats or ends. But can we simplify the square root of 18? We'll start to think of factors of 18. Are any of those factors, those numbers that divide into 18, perfect squares? And what we mean by perfect squares is this. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, etc. 5 squared is 25. First thing I do is by inspection, I look at square root of 18. I go, well, yeah, 18, it has a factor of 9, and 9 is a perfect square. So if I broke down 18 into the product of 9 times 2, then using properties of radicals, which allows me, when I'm multiplying, not adding or subtracting, okay, it allows me to break that apart and rewrite it as the square root of 9 times the square root of 2. Well, do I know what the square root of 9 is? I sure do. It's 3. So my answer is going to be 3 times radical 2. So this is an exact answer with radicals, whereas if you change this to a decimal, you wouldn't have an exact answer because you can't get one since that decimal representation never repeats or ends. All right, another way, if you want to go more slowly, which is fine, doesn't matter, you could take 18 and keep breaking it down. You could say, well, 2 goes into 18 because 18 is even. That leaves me 9, but 9 breaks down into 3 times 3. And the visual is that you see repeated factors in here, which in the final answer, when you're finding the square root, only one of those repeated factors comes out of the radical, leaving the 2, which does not have a repeated factor, inside here. So we need to do a little practice with simplifying radicals if we can. Okay, square root of 32. Well, if you put that in your calculator, that's an irrational number. But how can we simplify that? Well, I think about my perfect square list over here, and I think, well, are there any of these perfect square numbers, 1, 4, 9, 16, 25, that divide into 32? Sure, 16 divides into 32 twice. So from this step, if you see that the square root of 16 is going to come out as a 4, that's great. Go ahead and pull it out, and you're left with 4 square root of 2. So if it takes you a little bit longer to get here, that's fine too. Okay, if you need more help with simplifying radicals, again, I would reach out to, YouTube and look at some of those resources, Khan Academy or Patrick JMT. All right, let's look over here at the right column, complex numbers, kind of observe the similarities and the differences. You can see here that we have negative values underneath the radical. These are what we call complex numbers. These are not, these are what we're going to call imaginary numbers. And let's just define this lowercase I to represent an imaginary number. So what's an imaginary number? We have real numbers. They could either be rational or irrational, but then we also have imaginary numbers. Okay, and that's a special case when you have a negative underneath a radical. Okay, when you have a negative underneath a radical, we're going to end up with what we call an imaginary number. And we're going to use the lowercase I to help us represent that imaginary number. Okay, so how do we define I? Well, I, lowercase I, is equal to the square root of -1. So if I have a radical and it's the square root of -1, I can replace that radical with the -1 underneath it, called the radicand. I can replace it with I. So what we're going to do here is we're going to actually take -36 and rewrite it as -1 times +36. So that's a multiplication there. And then at this point, our properties of radicals still hold. I can take and find the square root of -1 and multiply it by the square root of 36. Well, at this point, now I see that I can replace I in for the square root of -1. And so now my attention needs to focus on this radical. Can I simplify it like I did over here? I sure can. The square root of 36 is 6. So I've got I here, and I've got 6 times 6 here. We don't typically write I times 6 like that. It's more common practice to put the I after the number, so I would have 6I. So just kind of compare these two answers right here. We have +6 here, but we have 6I here. Where'd the I come from? That suggests back in the problem that you had that negative underneath the radical. So let's take a look at what I call 25b. So when we had the square root of 50, our answer was 5 square root of 2. So what do you think the answer is going to be just because now I have a negative underneath the radical? And I hope you're thinking about, what that answer would look like. My answer is going to include a factor of I. So where do I place it in here? Well, common practice is to put the I after the 5. And our answer would be 5I square root of 2. So let's go through those steps. So I'm going to first of all rewrite -50 as -1 times 50. I'm going to break this apart. Negative square root of -1 times square root of 50. So I know I'm going to replace this radical with I. Now my attention just falls on what I did over here. And can I simplify this? Yes, I'd go through the same process here, and I'm going to get 5 square root of 2. So where do I put that I? Do I put it in front of 5? Do I put it behind the 2? Well, no, if you put it behind the 2, it might almost look like it's underneath the radical. So it's common practice to do 5 times the I times the square root of 2. So you try 27b. Observing the pattern that we have, okay, we have the square root of -32. Over here we have the square root of +32. That negative under the radical just suggests that you're going to have an imaginary number. And so that I is going to fit in between the 4 and the square root of 2. And you can go through the same process we went through here. You might want to first rewrite it like this. You don't have to do all this work if you see what the answer is, but just to have the structure there in place to help us. Again, replace that with I. Replace this with 4 square root of 2. Organizing this in a nice common practice format gives 4I square root of 2. All right, let's get ready for 1.5 and 1.6. And again, if you need a brain break, this is a good place to do it. Just pause the video and then come back, and then we'll finish these problems. All right, so down here we're solving for x. So I have x squared equals 9. Maybe you guys already know the answer is 3. Well, that's one of the two answers. There's actually two answers. I can take 3 and square it and get 9. I can take -3, multiply it by itself, and get 9 as well. So what's the mathematical process that's going to get us to those two answers of +3 and -3? Well, I'm going to rewrite the problem again. If I have x squared and I want to solve for just x to the first power, I'm going to undo the square power by bringing in the square root. There's a little understood 2 here that we don't usually show, but if I have x squared, I'm going to bring in a square root. And what I do to one side of an equation, I'm going to do to the other. And again, you don't have to write this little 2 right here because it is understood. So I brought in the square root on both sides of the equation. So now I'm working with an equation, so I have to keep it balanced. So bring in a square root on both sides of the equation. All right, well, here, when you undo this square by finding its square root, what you end up with is the absolute value of x. Well, the absolute value of x is equal to, let's move over here, the square root of 9 is actually 3. We've seen that. We just worked with square roots up here. 9 is a positive number, so we're going to end up with just 3, not 3i, because there's not a negative here. Okay, so now what do? We want to get x, not absolute value of x. Well, this kind of takes us to some background, some theory. The absolute value of a number is its distance from 0 on a number line. So let me just kind of come over here to the side and give you a little bit of background. So if you were told that a number is 3 units from 0, here's 0, okay, that number could be to the right of 0 at +3, or that number could be to the left of 0 at -3. Both these distances right here are 3. So the absolute value means a number's distance from 3. So when I remove that absolute value here, when this absolute value of x is by itself on the left-hand side of the equation, when I remove that absolute value, over here on the 3, I need to make the adjustment and say that the answer is either +3, okay, or the answer, the location could be at x equals -3. So we have two answers here, +3 and -3, and that's what we thought the answers were going to be by inspection. So you can see your answers, reported this way, stacked with the plus minus. Sometimes people like to put the smaller solution answer first and the larger solution second. Sometimes you'll see them write the two answers out separately, each giving them a label of x. Any of these representations of the answers right here are acceptable. All right, let's look at 29. Let's solve this equation. So I notice I have a square power. I want to get rid of the square power. So let me go ahead and rewrite the problem again. That allows me not to kind of crowd that original problem. Let me bring in the square root. And what I do to one side of an equation, I do to the other. What happens when you take the square root of x squared? Well, if it's an even exponent, like we did back up here, not if it's odd, if it's x to the third power, I won't be bringing in the absolute value. Okay, there's a lot of theory behind that, so my apologies for kind of like passing through that. I think that's just part of the online situation. But when you square root an x squared with an even power, I can get two answers, and the absolute value is going to allow me to get those two answers. So just kind of off to the side, if I had x cubed equals 18, I would bring in the cube root, an odd root, to both sides of the equation. Now, when you undo a cube power with a cube root, you just get one solution, and that's it. You wouldn't put absolute value around this. And then you try and simplify the cube root of 18, which I don't believe can be simplified. And so this would actually just be your final answer here. But back to our problem right here. We had an even power, not an odd power, whether that's a 4, 6, 8, or 10. Okay, no matter what, if it's an even power and you bring in an even root, you will have to put absolute value around your x. Any odd powers like 3, 5, 7, 9, when you bring in the appropriate root, Okay, that doesn't require that you have absolute value. There's only one solution for an odd power, but two for an even power. All right, so I've got the square root of x. Excuse me, I've got the absolute value of x. Okay, now let's look at the square root of 18. Well, we already did that work back up there at the top of the page. When you simplify that, you get 3 square root of 2. Am I done? No. Okay. This means a number's distance from 0, where there's 2 locations on a number line that you can be at that have a distance of 3 radical 2 from 0. So remove the absolute value, but make the adjustment to plus minus over here. And this would be a good answer right here, or you could list them separately or list them together with the smaller answer coming first. That's kind of common practice. Those are our solutions. Okay, let's change gears a little bit. Look at 30 and 31 and look how they compared problems 28 and 29. 30 and 31, these are already radicals right here. So they don't have powers. I don't have an exponent expression here, a power expression. Okay, so how do I solve this? So what number can go underneath the radical so that when I take the square root of it, I get positive 9? Well, you might be thinking, well, that should be 81. And you're right, the answer is going to be 81. But how do we mathematically support that? Well, I'm going to write the problem down again, just so I don't crowd the original problem. Now I've got a square root. Well, what's the inverse operation to square rooting something? Well, we're going to square both sides. So if I square that square root, I'm going to get the x out from underneath the radical. So let's square the right-hand side of the equation. So what's the square of a square root? Well, that's just going to be x. So no absolute value around here, just an x. I know that's an even power, but the situation is different up here. If I start with an even power and I bring in the associated root, the square root, that's when, in those types of problems, that I'm going to apply the absolute value around x. So when you bring in a power, you don't, even if it's even, you don't have to worry about the absolute value, whether it's even or odd. So squaring the square root, those two undo each other. I have x equals, and then we just do the computations or the work over here. So that's 81. And that's your answer. It's not negative 81. Try it. If you put negative 81 in for x, you're going to end up with a negative under a radical, and this answer should be 9i. So you can always go back and check your proposed solutions, or just kind of check something that you think is the answer in the original problem. Okay, let's look at 31. Okay, I got a square root of x. I don't want the square root around x, so I'm going to undo the square root by squaring both sides. So what you do to one side, you do to the other. So these two operations undo each other, leaving x. Go to your calculator, find the answer, and it's 144. Go back to the original problem, check 144. The square root of 144 is 12. Well, what if I put down negative 144 as a solution? Okay, well, the square root of a negative 144 would give us a 12i over here, just like we did at the top of the page on the right-hand side right here. Okay. Again, for this topic, solving for x, if you want to, Google something, if you need some more practice with it, there's a lot of resources out there for it.